Hello and welcome to today's tutorial. In this class, today we shall discuss about the class test 1 questions, that was more or less objective type, and it will be followed by discussion about the questions that we will raise in this class. So, first question was essentially a fill in the blanks question. It was an enhancement mode NMOS transistor with VTN is equal to 0.6 volt, has its source connected to ground terminal and 1.5 volt is applied to the gate. For VDD is equal to 0.4 volt, 1.0 volt and 3 volt. The transistors operates in the dash, dash and dash respectively. So, in what regions they really work, that has to be decided. As you know, if you look at the characteristics of a MOS transistor, NMOS transistor, if you plot say this is VDS versus IDS current voltage characteristics, it is somewhat like this. And a line which is which separates this is equal to VDS, VDS is equal to VGS minus VT. So, this particular line separates the linear region with the saturation region. This part is the saturation region and this part is the linear region. So, there are three parameters, one is your VDS, second is your VGS, third is your VT, that determines in which region the transistor is operating. Now, in this particular problem we find that your VDD is equal to your TN is equal to 0.6 volt and VGS is equal to 1.5 volt, these are fixed. That means, VT is equal to 0.6 volt, VGS is equal to 1.5 volt. Now, VDS is essentially the voltage that is applied across the transistor. Now, for in the first case when VDD is equal to 0.4 volt, then we find that VDS is less than VGS minus VT. That means, this is 0.4 volt and this is 1.5 minus 0.6, that is equal to 0.9 volt. So, since this is less than 0.9 volt, the transistor is in linear region. On the other hand, in the second case when it is 1 volt, so this is more than this VGS minus VT, so it will be in the saturation region. In the third case when VDD is equal to VDD is essentially the supply voltage across drain and source is equal to 3 volt, then also it will be in saturation. So, therefore, in this particular case the answer is it will be in linear region, saturation region and saturation region. Okay. So, this is the first question. Second question was, a transmission gate has an output voltage of 1.5 volt at a particular instant, assuming that VDD is equal to 5 volt, VTN is equal to 1 volt, VTB is equal to minus 1 volt and Vin is equal to 0 volt. The NMOS transistor is operating in the dash region and PMOS transistor is operating in the dash region. So, in this particular case you consider a transmission gate. This is the PMOS transistor and this is the NMOS transistor. Since the switch is transmission gate is on, that means, this is a 0 volt is applied to it and a VDD is applied to the NMOS transistor. Now, you have applied a voltage of Vin is equal to 1.5 volt here, 1.5 volt, this is your Vin. Now, and no sorry, output voltage is 1.5 Vin is equal to 0 volt, 0.0 volt, 1.5 volt. So, in this case what is the condition of these three transistors? Now, here we find this NMOS transistor we consider it as the source, this is gate and this is drain. Now, what is the gate voltage? Gate voltage VGS is equal to 5 volt. In this case gate voltage is 5 volt, and what is the drain voltage? I mean the VDS is equal to 1.5 volt, and what is VGS minus VT? That is equal to 5 minus threshold voltage is 1 volt. So, it is 4 volt. Therefore, in this case we find that VDS is less than VGS minus VT. So, what is the condition of the transistor? The NMOS transistor will be in linear region. What about the PMOS transistor? In case of PMOS transistor, we find that we can consider it as this one as source, this one as this one as source, this one as gate, and this one as drain. So, since this is source, this particular terminal is source, and this is 1.5 volt and this is 0 volt. That means, this transistor is in the gate is more negative with respect to source. Therefore, and since the threshold voltage is minus 1 volt, this transistor is definitely on. Now, in which mode it will be? So, in this particular case we find that the VDS is equal to 1.5 volt and VDS is 1.5 volt, yeah, minus 1.5 volt. And what about the VGS minus VT? What is the value here? VGS is equal to minus 1.5 and threshold voltage is minus 1 volt. So, it becomes plus. So, it becomes minus 0.5 volt. So, in this case what is the situation? This transistor will be, so this one this one is less than this one. So, therefore, this transistor will be in saturation, that means PMOS in saturation. Okay. So, PMOS will be in saturation and NMOS will be in linear region. Oh, I have written it just the opposite by mistake. Okay. So, here is a typo, that means it will be in linear region NMOS and PMOS will be in saturation region. Okay. Now, coming to the third question, delay in CMOS gate increases with the increase in fan in. So, how the delay of a CMOS gate increases both for NOR and NAND. In case of NAND gate, as we know, we have the NMOS transistors in series. In case of NAND gate, so here it is VDD, I have drawn a 3 input NAND gate. So, how the delay increases in this case? Delay, as we know, is proportional to n if n is the input. Therefore, I mean the pull down time is increased. So, pull down time increases by a factor of n with respect to inverter. Similarly, if we consider NOR, we find that the PMOS transistors are in series, whereas NMOS transistor in parallel. So, in this case the pull down time will not be affected, but pull up time will increase by a factor of n. So, it will be proportional to n. the pull up time. Therefore, we can consider we may say that in both the cases the delay is increasing linearly with the fan in. So, the answer is the delay of a CMOS gate increases linearly with the increase in fan in. Okay. So, the increase in delay that occurs in two different ways in two types of gates. In case of NAND gate it is because of the delay of the series NMOS transistors. In case of NOR gate it is because of the delay of the series PMOS transistors, that you have to keep in your mind. Coming to the fourth question, ring oscillators are used for what purpose, that is written here. So, ring oscillators are used for the measurement of delay, that is one of the primary application. However, although this is one of the most important application when a particular device is fabricated based on new technology, ring oscillator can be used as a clock. But you know that clock is not the primary application, because the clock frequency cannot be precisely controlled. Normally we use RC oscillator, or sometimes we use crystal oscillator, where you want a very stable fixed frequency. So, therefore, primary use is not as clock generator, although it can be used as clock generator, but it is routinely used for characterization of a device of new technology. In other words, it is being used for the measurement of delay. So, an N input static CMOS gate requires how many MOS transistors, and whereas a dynamic CMOS gate requires how many transistors. So, this is the question. So, as you know, an N input static CMOS gate requires 2 N MOS transistors if N is the number of inputs. For example, here this is a 3 input NAND gate, so we require 6 transistors. So, this is a 3 input NOR gate, we require 6 transistors, that means 2 N is the number of transistors that we require. On the other hand, whenever we go for dynamic CMOS, as we know, we require we can use either the PMOS network or the NMOS network. Whatever we use, say in this case we have used NMOS network, in that case we require these N transistor plus 2. So, in this case we require N plus 2 transistors. So, that is the answer. An input static CMOS gate requires 2 N MOS transistors, whereas a dynamic CMOS gate requires N plus 2 MOS transistors. Okay. Next question is, dynamic CMOS gates are about how many times faster than their static CMOS counterpart. We have explained that the increase in speed occurs because of two reasons. Number one is the number of transistor is almost reduced to half. Secondly, the capacitance that it will be driving, output will be driving, also reduces by a factor of 2. So, half reduction due to reduction in the number of transistors, and another half reduction because of the lesser capacitance. So, we may say that about 4 times increase in speed is possible, about 4 times. So, the answer is dynamic CMOS gates are about 4 times faster than their static CMOS counterpart. Next question is, charge sharing problem in dynamic CMOS circuits leads to some problem. What is the problem? Charge sharing problem in dynamic CMOS circuits leads to undefined output. So, we know that whenever a dynamic CMOS, say for example, here this one, we have a capacitor, load capacitance, and here 2 more capacitances are present. It may so happen that because of charge sharing, after redistribution of the charge which is stored during pre-charge period here will be distributed in these 3 capacitors, that will lead to reduction in the voltage. As a consequence, that voltage cannot be precisely defined. You cannot tell it high, you may not tell it 0. It all depends the relative value of the various capacitances and the way the charge sharing occurs. This is one the most important outcome of charge sharing, and of course, later on we shall see that charge sharing also leads to kind of additional power dissipation. For example, you have charged it to 1 and subsequently next output is also 1. So, in between during evaluation it will be it will discharge and again you have to charge. So, that will lead to kind of additional power dissipation, but primary outcome is undefined output. Next question is clock skew problem of dynamic CMOS circuits can be overcome using dash circuits. As you know, clock skew occurs because of distribution of the clock in the circuit and the next stage may receive the clock earlier than the preceding stage. It may so happen because of the clock distribution circuit, and that leads to clock skew problem, and you may get incorrect output. And we have already discussed this problem can be overcome by use of two types of circuits. One is known as domino CMOS or Nora CMOS. So, by using either of the two types of circuits, you can overcome the problem of clock skew. Then comes the swing restoration problem. Swing restoration logic raises the voltage level from this to this. So, swing restoration logic is used in pass transistor logic circuits. As we know, whenever you want to pass a 1 through a pass transistor, say VDD is input, here you have applied VDD and you will get here VDD minus VT, and here you normally put a swing restoration logic. Normally a weak PMOS transistor is connected to VDD and gate is connected to ground, and is this what is the swing restoration logic does is raises the voltage from VDD minus VT to VDD. So, the charging of this capacitor, which is essentially the gate capacitance of the next stage, will be raised from VDD minus VTN to VDD. So, that is the job of the swing restoration logic. It raises the voltage level from VDD minus VTN to VDD. Next question is streak path leads to some problem in pass transistor logic circuits. What kind of problem it can lead? Again, in this case it leads to undefined output. As you have seen, suppose you have a number of pass transistors and this is connected to VDD and these are all on, and you have another set of pass transistors through this is connected to ground, and so a snake path has been created here, and the voltage here actually will be dependent on the relative value of the on resistance of these NMOS transistors and the on resistance of these transistors. As a result, you will neither get VDD nor get 0. So, something in between, it may be VDD by 3, 2 or something, if the resistance is equal you will get VDD by 2 or something else, that will depend on the number of transistors in series in this part and this part. So, it again leads to undefined output in pass transistor logic circuits. Then coming to question 2, it was for the same area realization, the noise margin of a pseudo NMOS inverter is dash than that of inverter realized with an NMOS depletion type as pull up device. Write 2 lines in support of your statement. First you have to complete your sentence. For the same area realization, the noise margin of a pseudo NMOS inverter is better than that of inverter realized with an NMOS depletion type as pull up device, and the statement in support of this statement you have to write for the same area the resistance of PMOS transistor is more. As you know, PMOS transistor because of lesser mobility of holes with respect to electrons, for the same area a PMOS transistors will offer more resistance. As a consequence, the low level output voltage of pseudo NMOS is smaller, giving better noise margin. That means, say you are comparing a pseudo NMOS circuit. Here you have got NMOS network, sorry, this is connected to ground, this is connected to VDD, and another alternative is it is depletion mode transistor. So, this is connected to this, and here is your NMOS network, and this is connected to ground. Now, as you know, the resistance of this has to be 4 times of the NMOS network part. So, that you get a proper low level. Now, if they have the same area, then the resistance of this will be about 3 times, and as you know VOL is equal to the resistance of the NMOS network by the resistance of this plus this. Since this is more, the denominator part will be higher than the numerator, and as a consequence the VOL, that is the low level voltage, as you know in this case you do not get 0 voltage at the lower level. So, VOL will be lower in this particular circuit than this one, and as a consequence the noise margin of pseudo NMOS circuit will be better than that of using depletion type NMOS transistor as pull up device. Coming to the next question, for the same area realization, gates are better choice than type of gates are better choice than gates NAND or NOR. Write 2 lines in support of your questions. So, which gates are better choice than other type of gates? The answer is, for the same area realization, NAND gates are a better choice than NOR gates. And the statement that you have to write in support of this is, as NOR gates have PMOS transistors in series and NAND gates have NMOS transistors in series, NAND gates provides better provide a smaller delay and better noise margin, as I have already explained. While explaining this, this delay of this will be more than that of this, that is number 1, and as you know the noise margin is also better here, because as the fan in increases for the same area, initially the switching threshold voltage is lesser than VDD by 2, and then it moves towards VDD by 2, then goes it becomes more than VDD by 2. As a consequence, the NAND gates gives you better noise margin and also smaller delay, and as a consequence the NAND gates are better choice than the NOR gates. Coming to the last question, obtain ROBDD for the Boolean function f with the ordering A, B, C. Problem is f is equal to A exclusive of B exclusive of C. Use Shannon's expansion theorem to get the ROBDD. Here is the Shannon expansion. Let me expand it again. So, your f is A exclusive or B exclusive or C. So, first you have to expand around A, then you will expand around B and C. As you know, we can write it as A and B exclusive or C plus A bar B plus C bar. You can expand it this way. So, we see that by expanding this we get this one. So, this can be written as this, and then we expand around B. So, it becomes B exclusive of C is B dot C dash plus B C dot B dot C, yeah, plus A dash. So, this is essentially B C plus B bar C bar. So, expansion around B has been done. Now, you can again expand around C. This will give you A, B, C dash is nothing but C into 0 plus C dot into 1 plus B dash, this is C. So, C into 1 plus C dot into 0. Then this one again you can expand, A dot B C is nothing but B C into 1 plus C dot into 0 plus B dot C dot, if you expand it will be equal to C into C dot C into 0 plus C dot into 1. So, now you have fully expanded in the order A, B and C. Now, from this you can really draw your VDD. So, first you have to start with A and you will have two lymph nodes B and B. So, this corresponds to A and this corresponds to A bar. Okay. So, this is your output F. Now, from as you can see, A B goes to C, A B goes to C and that goes to 0, C bar goes to and C bar goes to A B, C goes to 0 and C bar goes to 1. So, we can write, we will have two more arms C and C, 0 and 1. These are the dotted lines and this is another dotted line. So, you can see if we follow this A B C dot 0 and A B C bar dot 1, A B C bar A B this is A, oh, that is A bar, no, this is A bar, acha, A bar, actually it should be A bar and this will be A. So, I have written it wrongly, this will be A bar and this will be A, okay. So, that was wrong, A bar this and A this, okay. So, that was the wrong thing. So, A, you can see A B C into 1, A B C 1. So, this is one path, then A B C bar 0, A B C bar going to 0, this path, this is complete. Then A B bar C goes to 0 and A B bar C dot 1, A B bar C bar goes to 1. So, that completes this path, these two paths, and similarly A bar B, then C goes to 0, this is complete. Then A bar B C bar, A bar B C bar, sorry, A bar B C bar goes to 1 and A bar B C bar goes to 1, that is complete. Similarly, A bar B bar, this is A bar, this is B bar, C goes to 1 and A bar B bar C bar goes to 0. So, that completes the VDD. Okay. So, this is how you can generate a VDD for any given function. I have expanded by using, I have shown it how it can be done by expanding the function using Shannon expansion. However, you can also do it by another approach where you can start with the truth table, then you can reduce remove with a full tree, you can VDD, you can start descent tree, then you can remove the redundant nodes and edges, you will get the same result. So, with this we have completed our discussion on the questions that that we have given in my tutorial, I mean the class test 1. Now, if you have any questions, please pass on to me. So, I have received several questions, let me discuss one after the other. First question is, let me read out super buffers, what is its use, number one question. Number 2 is how the characteristics will vary for transmission gate when it is driving a large capacitive load as it drives a small capacitive load. Okay, let me start with the first question, super buffer. Super buffer, as you know, main function is to drive large capacitive load. Now, when you are driving by using say standard gates like NAND and NOR, for example, let me use this diagram again. Say whenever you are using say NAND gate or NOR gate, we find that it is asymmetric in nature. Why it is asymmetric? Because this pull down time is longer than pull up time. Here pull up time is longer than pull down time. So, this asymmetry is removed by in super buffers. How it has been removed, that I have discussed in detail. That is number 1, because the driving capacity is increased. So, instead of using, I mean at the output of this you will put a super buffer that will drive a large capacitive load. So, here is your super buffer. So, here you will put a super buffer and that will drive the large capacitive load. This is number 1, that means the asymmetry is removed. Second is lesser delay. Why lesser delay? Because the delay in this case is more, because it is through a series of transistors, here also through a series of transistors, but in case of super buffer we have seen only one transistor is there, pull up and pull down. So, delay will be less. So, because of these two reasons, the delay of the super buffer, I mean you can drive a large capacitive load and delay will be small. That is the basic idea. In fact, the use of BiCMOS inverter is also for the same reason, that delay it has higher driving capability. So, delay will be less. Now, that answers the first question. Second is how the characteristics will vary for transmission gate when it is driving a large capacitive load, if it drives a and if it drives a small capacitive load. See, you see, we have already discussed the problem of driving a capacitive load with the help of a transmission gate. Say a transmission gate driving a large capacitive load and small capacitive load, what will be the problem? So, problem will be somewhat similar whenever you drive with a pass transistor logic circuit. So, whenever you drive it, obviously here it is more advantageous because you have two paths, and but here it will be only through one path. So, that means charging will be slower, that is number 1, because the charging current, as the for example, if this is VDD and this is VDD, and as the charge builds up, the current will keep on decreasing because the drain voltage is reduced, as you know, as long as it is in the saturation region, current drive is okay, but as it comes to the linear region, the current will gradually reduce through this and the consequent charging will be slow, and it will turn off when the voltage difference is here it is VDD minus VT. So, this kind of problem will arise whenever you are driving pass transistors. That is the reason why always you will find we use a instead of driving through pass register, we put a buffer or swing restoration logic at the output. A buffer is provided. So, this is the pass transistor logic, and at the output of pass transistor logic we put some buffer, and that drives the capacitive loads. We have seen the pass transistor logic family, DPL, SRPL and various other logic families, or that LEAP family. They always we have seen some buffers are at the output, are provided at the output to drive the capacitive loads. So, that problem is overcome by using capacitive loads. So, Shannon expansion theorem I have already explained with the help of this example. What Shannon expansion theorem does, say there is a function f1 f which is a function of say n variables x2, x3, xn. Now, you can write it in the form of this x1 f x1 plus x1 bar f x1 dash bar. So, what you are doing? You are expanding around the variable x1. So, in this case f x1, which is known as reduced function, is a function of the remaining variables. For example, here I have expanded around a. So, here you find that these are functions of the remaining variables. This is your b and c. Similarly, this is also function of the remaining variables. So, this and this will be a function of the remaining variables, and again you can further expand it as you have seen. So, this was around a, this was around b, and then you have expanded around c. So, you can see this is again a function of the, since only the 3 variables are there, obviously it will be constant. So, that is what you have got. That means, if you keep on expanding, you will get ultimately constants like zeros and ones, and that this is what is Shannon expansion. So, the Shannon expansion help us to generate the reduced functions, and also it can be used to get the pass transistor logic network. For example, once you have got this, you can map it to pass transistor network, because this will act like a 2 to 1 multiplexer, this will act like a 2 to 1 multiplexer, this will be like a 2 to 1 multiplexer. That means, each will be represented by a 2 to 1 multiplexer. That means, this A will be applied here and A bar will be applied here, and this is the output. Similarly, B you will put another pass transistor network, and this will correspond to A B and this will correspond to B bar. So, in this way you can form a pass transistor tree from this ROBDD, and you can realize the circuit. So, this is how Shannon expansion is done. Now, the question is, so this is a NAND gate. In case of a NAND gate, suppose you have a 2 input NAND gate. So, A and B, and it is realizing a function f is equal to A dot B bar, and as you know the truth table is A, B, F 0 0 1 0 1 0 1 0 1 1 1 0. So, that means if any one of the input is 0, output is 1, when both of them are 1, output is 0. Now, you can find out the probability of transition from one state, one input to another input. So, output can be, there are 2 possible outputs, one is 0, another is 1. You may say that this is the output state of this gate. Now, you can essentially draw a state transition diagram and the edges will show the probability of transitions. So, what is the probability of transition from 0 to 1? From 0 to 1 you see here you have got only 1 0 and here you have got only 1 1, I mean 3 ones. So, probability of transition from here to here is 1 by 4 into 3 by 4. That means, as we know P 0 to 1 is equal to P 0 into P 1. Okay. So, this is the probability of 1 and probability of 0 of remaining in 0. Now, what about this probability 0 to 0? So, here you know it has got only 1 0 and again probability of going to 0 is 1 by 4. So, out of 4 possibilities. So, this is the probability that it will go from 0 to 0, output will go from 0 to 0. Similarly, from 1 to 1 the probability will be 3 by 4 and into 3 by 4. Similarly, from 1 to 0 the probability will be 3 by 4 into 1 by 4. So, I believe this is what is the question. Now, the another question is NMOS depletion type transistor, here VGS is equal to 0 volts every time, but in paper there is some VGS is equal to V out. So, this is a question related to a depletion mode transistor as pull up device, and here you have got an input V in is applied here and you will get V out. Now, what will be the output? You see, whenever this is not a pass transistor network, in this particular case this is a NMOS depletion type, this is NMOS enhancement type. So, if you draw the characteristic curve of this transistor, it will be like this. And so far as this transistor is concerned, you have to draw it the other way, that means it will be somewhat like this. So, initially what will be the case? Whenever V in is equal to 0 volt, V in is equal to 0 volt, what will be the output? This transistor is off and this transistor is on. So, you will get VDD at the output. So, this is your this is IDS and this is VDS. So, initially the voltage will be here A, and as the voltage is increased above threshold voltage, as the voltage goes above threshold voltage of this transistor, then it will move to this point. Then as the voltage is increased, it will move gradually and ultimately it will reach this point, and this is the VOL. This is at that time both the transistors are on, and you will get a output voltage which is decided by the ratio of these two transistors. And the question is not very clear from this writing. Anyway, whatever is I have understood, I have explained. Here there is a question of driving a large capacitive load, say 1000 Cg. Now, question is, this is a point coming out from a pin, say this is a pin, from here the output is coming out and you have connected a capacitance Cg, I mean 1000 Cg. Now, what will be the delay in driving this? So, if you normally we put a inverter here, if this inverter is of unit ratio, I mean single, I mean there is no increase in size, width is minimum, length and width is minimum 2 lambda by 2 lambda, then what will be the delay? Then as we know the delay will be 1000 tau, 1000 tau. However, you are driving this from internally. So, we may say that there is some delay in driving this capacitance also. So, here it will be 1000 tau, and in driving this capacitance, assuming that this is also being driven by unit gate, I mean gate delay. So, here maybe an inverter is there. Driving this also will involve a delay of 1 tau. So, the total delay is 1001 tau. So, this delay in driving this capacitor and delay in driving this capacitor. So, here also you have got a capacitor which is equal to Cg. So, to drive this capacitor there will be a delay of tau, and to drive this capacitor there will be a delay of 1000 tau. Now, if you put several stages, like say first you have put this one, then you have put 10 times, then you have put 1000 times, then 100 times. So, this is 1, 10, stage ratio 10, and here is the 10 ratio 100. Now, you are driving this capacitance which is 1000 Cg. So, what will be the total delay? In driving this capacitance there will be tau, in driving this capacitance there will be 10 tau, in driving this capacitance there will be a delay of 10 tau, and in driving this there will be a delay of 10 tau. So, what is the total delay? 10 plus 10 plus 10 plus 1. So, it will be 31 tau. Okay. So, this will be the delay in driving this through these 3 inverters. Okay. So, I believe this is the question that has been given. Is there any other question? I think there is a question like this. I mean, here it is written how you are getting n by 2 E into 5 tau. Anyway, the question is not very clear what has been written. So, I cannot really answer unless the question is properly known. Any other doubt? You can pass on in writing. So, here there is a question about how you can simplify. Let me draw the VDD that has been given. Say A, B, this goes to B, from here it comes to C, it goes to C, C, it goes to C, then here 0, 1, 0, 1, 0, 1, 0, here it is 1. How to simplify this? As I mentioned, first step will be to merge the zeros and ones at the leaf line. That means, you have to follow a kind of bottom up approach. I mean, from the leaf nodes you have to go towards your towards the root node. So, how will you proceed? So, first step will be A, B, B, C, C. So, all the zeros are to be combined. So, let me write 0 here, let me write 1 here. So, 0 is coming from here, 0 is also coming from here, 0 is coming from here, sorry, 0 is coming from here, so I have written 0 is coming from there, and 1 is coming from here, 1 is coming from here, and from this one is going to again 1, and from this it is going to 1. So, this is the first step. After this first step, we find that means this particular 0, this is going to 0, this is going to 1, this is going to 0, this is going to 1, this is going to 0, this is going to 0. So, here also the last, this is going to 0 and this is going to 1. So, we find that all the C's are same, that means this C, this C, this C, this C, all the C's that has been given, that means the 0 is going to 0, 1 is going to 1 for all the cases. So, this will become A, B, B, and all the C's will merge. I mean not all, there will be two C's, one is your dot, another is your, from here it will come, here also dot, this will go here, from here also it will go here. So, this will go to both the cases 0 and 1. So, 1, 1, 0. Okay. So, here we again find that these B's, so this is 0, this is 1, and so what will happen in this particular case, B, this one and this one and this one and this one, this C, so this C again will merge because you can see these are identical. So, it will be same. So, that means I have omitted one step, this will be B, B. So, all of them, since these are this will merge, it will become one C, because this and dot all are going to C, and this is going to 0 and this is going to 1. So, this will disappear, and once this disappear, B will also disappear. So, in this particular function it will become A, B, B, and C will no longer be there, because directly the C will emerge and it will come here 0 and so that means the solid lines will go to 1, dotted lines will go to 0, this like this. Again we find that in this case also B will merge, A, B will merge and it will become single B, dotted line going to 0, solid line going to 1. Again it is independent of B. So, it will be A, dotted line will go to 0, solid line will go to 1 and it will become A. So, we find that from this after minimization and it is essentially equal to A. So, it is independent of B and C. So, A is 1 and when A is equal to 1 it is going to 1 and A bar is equal to 1 it is going to 0. So, it will realize a function A. So, this is a very redundant function. So, we find that all the edges and nodes are getting removed because of this minimization. Okay. So, with this let us come to the end of today's tutorial. Thank you.